welcome to part two. Today we're going to be now continuing to talk about um, whether a function is increasing or decreasing, and the previous piece of this lecture leads us to the first derivative test. So once we have determined the intervals for which a function is increasing or decreasing, then it's not that difficult to actually locate the relative extrema for the function, whether there's a relative max or relative min. So just recall that we had a relative maximum. If we had a function, let's say, that looked like this, and then let's say this is the interval a to b, then we could say that there's a relative maximum here at a because this is the highest point on the interval, and there's a relative minimum at b, f of b here, because that is the lowest point on the interval. Now, we will use this so-called first derivative test to actually figure out whenever we have a max or a min without having to actually graph the function. All right. So, for example, if you're given, like, let's make this more concrete. Let's say you're given a function that kind of looks like this. And instead of being on an interval, it goes up and down infinitely. And let's say this is the origin. Let's say this is the point 1. Let's say down here we have -1, and let's just assume that this was run perfectly, and this is, let's say, -1/2, just to make it look a bit nicer. So if you're looking at this function as a whole, from -infinity to infinity, we know that this function eventually goes up forever, so there's no absolute maximum, there's no absolute minimum because it keeps on going down. However, there is a relative maximum at the point 0, 0, because it's the highest point on some interval, and we have a relative minimum right here because that is the lowest point on some interval. All right, this is the relative max and min. Now, to say this even nicer, we can say that the point 0, 0 is a relative max. This is really the reason why it's a relative maximum, because the function is increasing immediately to the left of 0, 0 and decreasing immediately to the right of the point 0, 0. This is the same as this point down here, let's say 1, -2. This is a relative minimum because the function is decreasing immediately to the left of 1, -1/2, and it's increasing immediately to the point, immediately to the right of the point 1, -1/2. Now, this leads us to the first derivative test, which will make this a little bit more explicit, and it will actually give us a nice method for finding relative maximum or minimum of any function that you're given. So this is the most important part of this lecture, this theorem. This theorem will be definitely on your final exam. All right, so theorem. This is called the first derivative test. So if you need to look it up someday, remember that there is a so-called first derivative test. Okay, it says the following. Let's C be a critical number of a function f that is continuous on an open interval I containing C. containing C. If f is differentiable on the interval, except possibly at C, then f of C can be classified as follows. Number one, if f prime of C, if the derivative, well, if f prime of x, if the derivative of x changes from positive to negative, from positive to negative, then at C, from positive to negative at C, then f has a relative maximum at the point C, f of C. Okay, so if the derivative changes from positive to negative at C, then the function f has a relative maximum at C. 2, if the derivative of f changes from negative to positive at C, then f has a relative minimum at the point C, f of C. And finally, if the derivative of f is positive or negative, let me do it this way so it's not confusing. If the derivative of f is positive on both sides of C, or negative on both sides of C, then f of C is neither a relative max nor a relative min. So let me illustrate what's going on. So let's say you have a function that looks like this. Let's say C is a point here and the function looks like this. Right? It's a parabola. Let's say this point right here is f of C. If we look at this from left to right as we go to C, we see that this is decreasing, and then as we go from left to right to the right of C, we are increasing. So here we are decreasing, here we are increasing. If you notice, we're going from negative to positive. Because remember, from the previous section, we know that when the function is decreasing on an interval, then that means that the derivative is negative, and when the function is increasing on an interval, that means that the derivative is positive on that interval. So we're going from the derivative being negative to the derivative being positive. And by number 2, if the derivative changes from negative to positive at C, then we have a relative minimum at this point. So this is the relative minimum. So that will be your relative minimum situation. In contrast, if we have now a parabola that looks like this, right? Say c is here and f of c is up here. Not make it so high. Now we can see that when we move on the function from left to right, from left to right, in this direction, the function is increasing, which means that the derivative to the left of c, so to the left of c here, the derivative is actually positive because we are increasing. And to the right of c, the derivative is negative because the function is decreasing. We could clearly see that. And because the derivative is going from positive to negative, then by number 1, because the derivative is changed from positive to negative, we have a relative maximum at this point up here. So this is a relative max. And finally, the case for which the function just keeps on increasing or just keeps on decreasing will look like something like this. So let's say c is here, and let's say you have something that looks like this, kind of goes up and then up again. It doesn't really go down. So let's say c is here, then from left to right to the left of c we're going up, and then from left to right to the right of c we're still going up. So there is no relative max there, nor min. And similarly, let's say you're going down, let's say you're going down like this, then let's say c is here, then to the left of c you're going down, so that means that the derivative is negative, but to the right of c you're also going down, so the derivative is still negative, so there is no minimum nor max. So no relative max or min in this situation, and no relative max or min in this situation either. And I don't think I wrote it. Oh yeah, I did write it. Relative maximum here. All right. So these are very important for us to know because they will help us figure out when where a function has a max or a min. Now, let's actually do an example before I spoil all the surprises that are to come. I feel like spoiling them now. It's actually one of my favorite parts of Calc 1, this part right here. Okay, so example. Let's find the relative extrema of the function f of x is equal to 1/2 x minus sine of x in the interval 0 to 2 pi. All right, so first of all, we're asked to find the relative extrema. Now, I don't know about you, but I don't feel like graphing sine of x, 1/2 times x minus sine of x. It does not seem like the best function to graph by hand without using a calculator. But we can hopefully apply the first derivative test to actually find all the relative extrema of the function. Now, what needs to be true? Well, first of all, to be true, we need to have a function that is continuous on an upper interval containing c. We also need that function to be differentiable on that interval. Well, let's look at the function 1/2 x minus sine of x. This is not a polynomial function. This is not a polynomial function. However, this is a composition of two continuous functions. We saw this when we spoke about continuity. We saw that if you take two continuous functions and you add them up, their composition is continuous, their sum is continuous. So we know that the linear function 1/2 x is continuous everywhere in its domain. Sine of x is continuous also everywhere in its domain. So if we add or subtract two continuous functions, what we get is also a continuous function. So f is actually continuous in its domain. Now, we also know that sine of x is differentiable everywhere in its domain, and 1/2 times x is also differentiable everywhere in its domain. So this composition of differentiable functions is also differentiable. We saw this when we spoke about the power rule. If you have f prime of x plus f plus g prime of x, this is also differentiable. Okay, good. So before we could begin to talk about the first derivative test, notice that we need to find out when the function changes from positive to negative or negative to positive. Now, we need to find the values of c. To find the values of c, we need to actually find the critical numbers. So to find our values of c, we need to find critical numbers. Again, critical numbers happen when the derivative is equal to 0 or does not exist. So what do we need to do? We need to solve the equation f prime of x being equal to 0. We don't know what f prime of x is because we have not computed the derivative yet. We could find that out now. So let me just rewrite f of x. F of x is equal to 1/2 x minus sine of x. That means that the derivative of x is equal to simply 1/2 minus the derivative of sine is cosine, so minus cosine of x. Okay, so now going back to this problem here, to find the critical values, we have to solve for when the derivative is equal to 0. Well, we know what the derivative is, so let's substitute in what we just got here, which is 1/2 minus cosine of x equal to 0. Well, I could move the cosine to the right side, and I get, by adding cosine on both sides, so I get 1/2 is equal to cosine of x. And I'm just going to rewrite this to the more standard cosine of x is equal to 1/2. Now, if you don't remember your trigonometry, now will be a good time to actually do some review. We know how the graph of cosine of x looks like from 0 to 2 pi. We know it begins at 1, goes down to -1, and then it goes back up to 1 on this interval. This not to scale, by the way. So at pi over 2, we have that cosine is equal to 0. At pi, cosine is equal to -1, and at 2 pi, cosine is equal to 1, and at 3 pi over 2, cosine is equal to 0 again. Now notice that 1/2 is a number that's here. And if you were to draw a horizontal line here, you will see that we cross the graph of cosine twice. Right before pi over 2 and a little bit after 3 pi over 2. Now, if you remember how to use the right triangle trigonometry, the reference triangles, and in particular the unit circle, you'll figure out, and I'm not going to spend too much time doing that, you will figure out that cosine of x is equal to 1/2 on the interval 0 to 2 pi when x is equal to pi over 3 and when x is equal to 5 pi over 3. Okay. Now, again, you could use the reference triangles, you could use the unit circle to actually figure this out. This is not too difficult to do, but this is again from trigonometry. Okay, so now that we have this, these are our critical values. Also, we should always check that these values actually fall on our interval. You know, pi over 3 is definitely bigger than 1 but less than 2 pi. 5 pi over 3 is definitely bigger than 0 and less than 2 pi. I think I said 1 for pi over 3. It should be 0 because that's the interval that we're working with. We're working on this interval. And that's why I didn't include, all the other numbers, because remember, the graph of sine keeps on going up and down on both directions. So you are actually 1/2 at an infinite amount of points. So that's why we are limiting our domain. Okay, so now that we have our critical numbers and there are no points for which the derivative of x does not exist, you could plug in any value here for cosine and you always get an actual number. We can conclude that these are the only two critical numbers on that domain. Now comes the fun part. Now we have to figure out when f is increasing or decreasing, and then once we figure out where f is increasing or decreasing, we have to make a determination of whether or not we have a relative max or min at these two critical numbers. Now, in the previous part of this lecture, I mentioned the technique of actually using a table. For this part of the lecture, I'm actually not going to use the table because I prefer to use this following method. So what I like to do is I simply write out the real number line. And I write out my domain. I'm working on from 0 to 2 pi. I know that I'm working with pi over 3 somewhere here, and I know that I'm working with 5 pi over 3 somewhere here. From the graph up here, we know that pi sits somewhere in the middle of these two values. We know that pi over 3 is certainly less than pi over 2, so maybe I should make this a little bit more to scale. So let's say this is pi over 2. So let's say pi over 3 somewhere here. Let's make this look a little bit better. So let's say 2 pi is here. Let's say 3 pi over 2 is here. So let's say that 5 pi over 3 is here. All right, so why am I doing this? Well, now I can actually talk a little bit more about my intervals. Now, I'm working on the interval 0 to 2 pi, okay? 0 to 2 pi. And this was given to me as an open interval. I think I wrote it, I wrote it as open. I'm using closed interval notation here, but I do not mean that this interval is closed. I'm just focus on these two lines. Okay, so we're working on the interval 0 to 2 pi. I have two critical values, pi over 3, 5 pi over 3. So what I'm going to do is I'm going to break up this interval into 3 pieces. Those pieces will be the interval from 0 to pi over 3, the interval from pi over 3 to 5 pi over 3, all the way up here, and then the interval from 5 pi over 3 to 2 pi. So I call this I1, I call this one I2 for interval 2, and this I3 for interval 3. All right, this looks convoluted for now, but we'll clean it up in a second. So let me just redraw this again. So we have 0, pi, 2 pi, 3 pi over 2, 5 pi over 3, pi over 2, and pi over 3. All right, so what am I going to actually do? Well, what I'm going to do here is I am going to find test values, and the test values have to be inside of these intervals that I called I1, I2, and I3. So I need a test value, I'm gonna call it x1 here. I need a test value, call it x2 here. I'm actually just gonna pick pi because it's right there in the middle. And then I need a test value here, x3. This is the same thing as we did with the table in the previous step. But I like to actually write everything on the real number line. And again, you will see why in a second. All right, now that I have my test value, let's say for x1, what's a value that I know for certain is less than pi over 3? Well, one easy value will be half of this distance. I know this is not at the half point. This is actually very close to pi over 2. So half of pi over 2 is pi over 4. So I'm going to pick pi over 4 here. On the other side, between 3 pi over 2 and 2 pi, I know here I have 5 pi over 3. So, if I move a little bit further here, I could pick the test value, let's say 7 pi over 4. I'm simply writing this in terms of force now. Okay, so I just took the distance between 2 pi and 3 pi over 2, and took the half of that. All right, now that we have our test values, we have to plug into the derivative. So I have to find out, when I test, I have to find out what f prime of pi over 4 is, what f prime of pi is, and what f prime of 7 pi over 4 is. All right, and remember, we're interested in the signs more than the actual value. So this is what I was calling x1, this is what I was calling x2, this is what I was calling x3 in this image up here. Well, I know what the derivative of the function is. The derivative of the function is 1/2 minus cosine of x, but in place of x, I'm putting pi over 4. All right, well, what do we get here? What is cosine of pi over 4? Again, if you don't remember how to do this using the unit circle, you could use the reference triangles and turn that pi into 180, and then do 180 divided by 4, and then you can figure out what the angle is if you don't remember how to use the unit circle. In any case, cosine of pi over 4 is actually, let's see, cosine of pi over 4 is I'm really gonna have to use my reference triangles. Nope, yeah, let's just draw them. This way I feel much better drawing them. Alright, we have one right triangle here and another one here, size 1, 1, radical 2, and here we will have the following. We have, I always get confused, 1, 2, radical 3. So it will be 1, no. 1, 2, radical 3. Let me just make sure that is correct. Yeah, that is correct. All right, so the angles are as follows. So this is a 60-degree angle, 30-degree angle, and then this interior angles are 45. All right, so if I have pi, we could say pi is equal to 180. So we have 180 divided by 4, which is going to be equal to 45. So we're dealing with, so this implies pi over 4 is equal to 45, and this way I like using the reference triangles. So now I simply pick, okay, what is cosine of pi over 4? Well, I look at cosine of 45 degrees. Cosine is adjacent over hypotenuse. So the adjacent angle is radical 2. Radical 2 is 1. And the hypotenuse is radical 2. So it's going to be 1 over radical 2. So it's going to be equal to 1/2 minus 1 over radical 2 here. Now for actually pi, we get this one from the general form, and we have that this is minus 1. So here we have 1/2 minus 1. And then for the last one, again, using the reference triangles, we have 7 pi over 4. Well, this is the same thing as 45 times 7, which is 315. And now if you were to look at this, you could do 315. You could do 360 minus 315. So this is 360 because it's a whole unit circle minus 315, and that will give you 45. All right, and from the previous one we know what the cosine of 45 is. So we have what we have is really 1/2 minus cosine of 7 pi over 4. That's equal to 1/2 minus 1 over radical 2. I don't like memorizing the unit circle. I actually prefer using the reference triangles. But if you're somebody that does like to memorize the unit circle, it is very useful. There's also tables that you can memorize for this. But I've always liked using the triangles. I think it's a more effective method. In any case, we do have to simplify this. So I don't care about the simplification, to be honest. I just care about the sign. So 1/2 minus 1 over square root of 2, what will that be equal to?